All right, my energy is starting to wane, guys, so this is for sure the last video, no matter how much I get done talking about this stuff, but I think it should suffice. So the last one where we look at trig with computational continuity. This is different because I throw a root in there, which basically means like the domain is restricted here because anything under the square root has to be 0 or bigger. C squared, cosecant squared x plus 7, it has to be greater than or equal to 0. Now, when I was a student, I didn't do a lot of reflection on problems like this. I was just sort of like, all right, what's the method that I can do some algebra to get the answer? But now that I'm a little bit older and maybe a little wiser, I think about this and I say, what is the inherent nature of this number? A fancy way of saying, can I just tell when it's positive or negative just by looking at the expression given to me? And the answer is, yeah, you can. Think about whatever cosecant of x equals. Remember, cosecant of x looked like this. It was basically using the sine function to piggyback kind of some parabolic looking type things, which means this thing exists everywhere above 1 and everywhere below -1. So think about those values. I take something that's either above 1 or below -1, and I square it. I multiply it by itself. What happens when you square numbers? They're always positive. So think about cosecant squared x and an ever positive number, and I add 7 to it. When is that greater than or equal to 0? It's always greater than or equal to 0. Yeah. So that might lead you to believe it's continuous everywhere. Except it's not. Because the cosecant, just like on the secant of x in the previous problem, it messed up the fundamental aspect of where can these things exist. There are still going to be asymptotes for cosecant squared x plus 7. So you got to think to yourself, all right, we're actually talking about 1 over sine squared x plus 7. That's really what's happening inside there, which means the bottom can't be 0 here. And again, if I just square root both sides, sine of x can't be 0. So yeah, it's kind of like on the surface there's an absence of discontinuities. But when you think about it, if cosecant lives there, then that means sine cannot be 0. And it can't be 0 at what? Pi n, all right? So you have non-removable discontinuities at x equals pi n. All right. Now, there's one more, I know this is a lot. There's one more thing I wanted to talk about. And it's actually the first 4 problems on your homework assignment. So it kind of feels like you have to watch all 4 of these videos before you can even start doing number 1. Okay, I'm not sure how this is going to work. Oh, I know what to do. All right. That was probably pretty painful to watch me try to do that. All right. So here's what we're doing. We're saying, basically, here's our function. It goes from here to there, close circle, open circle, close circle, and it never quite goes beyond 1, 2, 3, 4, 5, x equals 6. What I'm asking up here is I'm saying, take this function and ask yourself, on which of the following intervals, so here are the instructions. On which of the following intervals is this function continuous? All right, so I'm just, you know what, maybe it's a better idea if I just leave it like this, and we'll look at it as, here's x equals -3, here's x equals -1, here's x equals 1, and here's x equals, wait, was there a 4 in there somewhere? Oh yeah, we're good, we're good. Okay. Thank you for bearing with me. I really do appreciate it. All right, so the question is, on which of the following intervals, if any, is the function continuous? So, you know how I was talking about how limits from the left and the limits from the right talk about, they really inform continuity. Well, this kind of illustrates the fact that you can have continuity from the left and the right, but maybe not at a specific point. In describing, you know, like an interval where it's like, we're continuous, but if you go beyond there, you got to break up that continuity. So let's get right to it. The brackets mean include. The parentheses mean exclude. All right? So let's think about it. From here to here, is x equals -3 to x equals -1, is our function completely continuous from -3 to -1, including the endpoints? The closed circles indicate yes. So what I'm doing is I'm circling the ones that, yes, it is true. What if I said -3 up until just before -1? Is this continuous from x equals -3 to x equals -1.000000001? Is it continuous from here all the way to there? And the answer is, yeah. So it doesn't matter if there's a parenthesis on the -1. If it included the -1, it's still going to be continuous even if you don't include the -1. And then the same logic can be argued for these last two. Is this continuous from -2.99999 to -1? Yeah, it is. And then if you don't include either endpoint, it's still continuous from almost -3 to almost -1. So on that first row, circle them all. All right, now I am going to get this out of the way so it's not in our way. Focus on -1 to 1. Is it inclusive -1 to 1 continuous? Nope. The open circle means you do not include 1. So, anywhere where you bracketed 1, it is not going to be continuous on that interval up to 1. Okay, so that leaves out both of those. However, yeah, it's good all the way up until 1, but not including it, which is what the parenthesis means. So it works both for F and for H. again, if you need to, go back and pause it and ponder it. On this next one, we have open circle to open circle. All right, that takes away any brackets for any of them. So it's not I, it's not J, and it's not K, because we're not going to bracket the 4 or the 1, and certainly not both of them, since they're both open circles. Now, somebody might be like, well, what about that closed circle at 4? Well, the function is continuous from here to here. When it jumps down, it creates a new interval, which we are not discussing right now. But from 1 to 4, not including, all right, not bracketed but parenthesized, we would include part L. So right now what we have circled is A, B, C, D, F, H, L. Okay, last one. Again, I'm gonna erase this so that we can get a little clearer picture of just the thing in question. And I would erase that open circle there. It is no longer talking about starting at x equals 4, because this is where it picked up. Now, does an asymptote include? No. So anywhere where you're trying to include x equals 6, here and here need to be excluded. Now, this is kind of tricky because somebody could make the case that an open circle means it comes up all the way up until the circle, but then the asymptote means it's forever getting closer. But those two concepts are actually exactly the same idea. It's you're getting infinitely closer to the asymptote, but never reaching 6. If this were just a straight up circle like that, it's the same idea. You're getting infinitely closer to x equals 6, but in sort of like a nice, neat linear pattern that's approaching a specified y value. So, I guess what I'm saying is, if you're going to use the logic that an open circle means we can use a parenthesis to talk about continuity, then you got to use the same logic to include an asymptote in the continuous nature of it. So, if 6 is parenthesized, I'm going to include it. So, bracket for the 4, but also a parenthesis for the 4. Because it'd be kind of like, hey, from here to there is it continuous? Yeah. Okay. So, that's computational continuity. This was a pretty rigorous approach by which to make these videos, so this isn't obvious to you guys, but I've given you a lot of examples. Please communicate with me what questions you have, and I only have one more new assignment for you guys next week. It's going to be a comprehensive review of everything we've talked about in terms of limits and continuity. Okay, so it's basically like a review. And yeah, so contact me when you have any questions and we'll figure this stuff out. See you guys.